Today we're going to be working on applications of exponential functions. These are real-world scenarios where exponential functions apply. So the first thing we're going to do is practice identifying growth and decay functions. And you can see on your page you have some examples of growth and decay functions. And remember that the way that we identify growth or decay is based on the growth or decay factor, the base of the function, the number that's holding up the exponent. So I'm going to go ahead and highlight the base for each of these functions. Again, we're identifying the number that's holding up the exponent. So for example A, the base is greater than 1, so this is a growth function. For example B, the base is a fraction with a value that's between 0 and 1, that's 5/7. So that's decay. For example C, the base is 1.4, so that's a growth factor. For example D, the base is 0.99, so that's a decay factor. And for example E, the base is 1.01, that is greater than 1, so that is a growth factor. Now I want to talk for a few minutes about growth factor versus growth rate. The base value in each of these tells us whether the function is growing or decaying. However, the growth rate or decay rate tells us how fast it's growing. So we're going to take a few minutes to talk about that. So when we're talking about growth factor, which is the base of our function, we are looking at the number that's holding up the exponent. So I'm going to give an example of this. Y equals 8 times 1 to the x. So in this situation, our base is 1. I'm going to make a table of values and evaluate this function for a few values of x. So I'm going to do 0, 1, 2, and 3. So 8 times 1 to the 0. Anything to the 0 power is 1, so 8 times 1 is 8. Then I'll do 8 times 1 to the first. 1 to the first is 1, and 8 times 1 is 8. 8 times 1 squared. 1 squared is 1. 8 times 1 is 8. 8 times 1 to the third. 1 to the third means 1 times 1 times 1, which is still 1, times 8 is 8. Notice that when our base or our growth factor is 1, the values of y don't change. We're just basically getting 100% of that leading coefficient number each time. It's not increasing, it's not decreasing. It's just 1. If we want the values of the numbers to increase, we have to add something to that base number to get a greater than 1 base or growth factor. So let's work with y equals 8 times 1.5 to the x. So now our growth factor is 1.5. So let's create a table for this. So I'm going to substitute the same values. 8 times 1.5 to the 0 power. So anything to the 0 power equals 1. So 8 times 1 is 8. Next, we'll do 8 times 1.5 to the first. This is taking 1.5 to the first power, which is 1.5, times 8, and that is 12. Next, we'll do 8 times 1.5 squared. 1.5 squared times 8 is 18. And then finally 8 times 1.5 to the third is 27. Let's take a look at what's happening here. These values are growing because it's taking 1 times 8 plus an additional amount that we've added to each one. So if I look at this first one, not that 1.5 to the 0, but 8 times 1.5 to the first, I'm getting 100% of 8, so 100% of 8 plus another 50% of 8. So 100% of 8 is 8, and then 50% or half of 8 is another 4, and that's how I got 12. Of course, we can evaluate this with our calculator, but that's the math that's happening here to get this value for 1.5 to the first. If I look at the third value here, this is taking 100% of the new value, which was 18. So we moved on to the next and the next and the next. So this is taking the previous value of 18, 100% of that, plus another 50% of that. Half of 18 is 9, and adding those two together to get 27. So each value is growing by 100% and another 50%. So we're adding half as much each time as we move forward. And so this 1.5 growth factor is causing growth in our function each time. And the growth begins to spread rapidly. So we see that exponential growth happens very quickly, and that's why the graph becomes very steep. So the growth factor is the entire total of the base value. But the amount that we're adding each time, this additional 50%, that's our growth rate. And so the rate that's being added, or the amount that's being added, is our growth rate. In this case, it's that 50% that's being added to the 100%. Here's our 100%, and then the 0.5 is our growth rate. So now let's take a look at the examples that we've been given on the front of this page and talk a little bit about the setup for growth and decay functions in the real world. So hopefully you noticed with the examples that we did to the right, the leading coefficient was our initial value. And so whatever number is sitting out in front of your function will represent the starting value of your function. And that's true for all exponential functions where there are no horizontal or vertical shifts. And so these are in general form, and that applies here. So our A will be our initial amount for both growth and decay functions. And then our growth factor will be the entire base of our function. So whatever's inside of here, this whole thing, adding or subtracting some amount, will be our growth factor. Now within that growth factor, we have our growth rate. And so the growth rate will be whatever amount we have added or subtracted to create a growth or decay function. And so our growth rate, R, we'll use it as a decimal in decimal form inside the parentheses with the 1, but when we define the growth rate or decay rate, we can also write it as a percent. And then Y is just the final amount after we have substituted into the equation our initial value and our growth rate, and then some amount of time that the function has been allowed to grow or decay. So we've got our time up here, and we'll substitute a value for that as well. So let's look at a couple of examples of this. So we're going to be finding growth and decay rates as well as the other important parts of these functions. So for example 1a, our growth or decay factor is 1.03. And since this number is greater than 1, this is a growth function. The initial amount is our leading coefficient, 3.5. So at the start of this function, or on the y-axis, we would see the 3.5. The growth factor, the growth factor is 1.03. And so the amount that has been added to that 100% is 0.03. Now, if we want to change from a decimal to a percent, we move the decimal point 2 places to the right, which gives us 3%. So our growth rate could also be expressed as 3%. Our next example, our base value is 0.95. This is less than 1, so this is a decay factor. That is our decay factor. The initial amount is our leading coefficient, 10,000. And then we'll find our decay rate. So for our decay rate, basically that base is 1 minus r, because we're subtracting, the number is decreasing to 0.95. An easy way to think about this is that the 1 is like 100%, and the 0.95 is 95%. If I have 100 and I subtract some percentage and I end up with 95, what would that R value have been? That rate is 5%, or 0.05. Turn the page and try example 1, C and D on your own. Then proceed to the next video.